So here we study another example where we have applied the facility in the Quasar software for creating an external cross-section. The sample consists of a layer of titanium deeply buried under aluminum overlayer. Synchrotron radiation was used to study this because the depths are very large, so we need a high IMFP to be able to study this structure. The the XPS electrons from titanium pass through the overlay of aluminum, and the cross section for aluminum and titanium are very different. And therefore, as we shall see shortly, this requires a careful choice of the cross section for an accurate analysis. So we load the spectrum. The spectrum is here, titanium. So this is titanium 1s from this sample, taken at a photon energy of 8,000 electron volts. Here's the peak. These are plasmon structures, and here's the background. So now we analyze that. We analyze, hit analyze, and we need an IMFP. I'm already loaded that here. The peak is at 3020 eV roughly, and for aluminum we have an IMFP of 58 angstroms, as you see. For titanium, has the same energy, we have 51. So 51, 58, that's about 54. So we put in 54 for the IMFP as the average value. And now we analyze this. Now, if we use a universal cross section, we increase the thickness here and increase here, decrease here, and one more down here. We have a reasonable account for the background over the full range here, but not in this range. This is the range where we have the plasmon structure, the aluminum plasmonous. We see that we get 4 nanometers to 36 nanometers, where the start depth is much closer to the surface than what we expect. But we do get the right structure, the sequence of aluminum being on top, and we have a layered structure here. But we can do better if we can account for this part here. To do that, we could change from the universal to the external cross section. And again, as we have a sharp plasmon structure here, we will use a 3-parameter cross section. Now we see the plasmon is here and it's here in the spectrum. So we need to move that over to line up with that. So we increase or decrease the C value here until it lines up. And that's about here, right? And now we rescale this to get a better count. And now we fine adjust these values here. Probably sharper plasmon here, maybe like that, and maybe like that. So this is fairly close now to the spectrum, and we account reasonably well for the plasmon structure and the background out here. So the conclusion is that it goes from 14 nanometers to 36 nanometers. Now the start depth is at 14 nanometers. That's very close to the nominal value of 15 nanometers, whereas the end depth is somewhat larger than expected. We could, instead of using the 3-parameter cross section here, we could also use a blend of cross sections. So we could take cross section valid for titanium and one for aluminum and make an average of these. This is what you can do with this facility in the software here, the blend of X sections here. Let me illustrate that here. You click blend of cross sections, and then we click OK here, and then we find the cross section. In the list of cross sections, we have the different cross sections here. This is the standard aluminum, germanium. The metal oxide here is the universal cross section, 2-parameter universal cross section. We have for the polymers and the silicon dioxide. We also have a cross section here that I've stored valid for titanium that we determined in a separate experiment. So now we could try to make a blend of this cross section, which would be representative of the titanium layer, and blend that in with a cross section. I click here to have 2 cross sections. I click OK here, and then I load the aluminum cross section here. Because we have a layer of titanium, we have a layer of aluminum. To blend in these, we re-normalize these so we get an area 1 here. Cross section. You see the aluminum has a very sharp plasmon structure here, around 15, 16 electron volts. So we have given them equal weights of about 0.5. We re-normalize the weights here, and we see the result over here, and the agreement is fairly good. We could change a little bit, maybe we get 15. We'll get closer to 15 than with the other one, but the end death seems to be around 360 as well. We could also use simplex here, maybe in this range, to see what that gives. And it gives slightly different values, but very close to these values. And they are very close to what we got with just adjusting the 3-parameter cross-section. The end result doesn't vary much from that. And in general, one should probably not spend too much time on trying to optimize these parts, because the end result is not too sensitive to that. However, we did do that in this paper where we changed the relative weights of the titanium and the aluminum cross sections for each sample, and tried to find the cross section which gave the best fit to the background, and in this way determined more accurate values for the start and end deaths. Now suppose you didn't have the cross section for titanium available. I'll illustrate how you can use the universal cross section instead of the titanium cross section and get about the same result. Let's do that. We have the universal cross section here. Switch to external cross section and make a blend of cross sections. We read in cross section 1 from the file here, the X sections here, and the universal cross section is this one, X metal plus oxide, because it's a good approximation for all the metals, the transition metals and their oxides. So it would be, we expect it to be a quite good approximation for titanium as well. So we load that here. We take another one, second cross section, and that was the aluminum cross section. So we load that here. We give them equal weights as before. We renormalize the weights. And now we do the analysis. And you see we get about the same as we had before. Maybe slightly larger, 17 nanometers, 16, 17, in that range there, 16 nanometers. So it's close to what we had before and close to the nominal value. The end death, as before, is larger than expected. You'll also see another thing here, which is in general true for all the cross sections that we have graded, that the sensitivity of the analysis to the end death is rather small. So you see, if I change this, increase that, it doesn't change much here. Maybe slightly better here than here, but the change is really very, very small until we get down to about 300, 280. It's very sensitive, whereas the start depth is much more sensitive to the value here.